Yesterday, Ida talked about hierarchical clustering. So the idea was that we read some data, right? And then we compute the distances between the data. We would take a pair of data instances and then compute something. So Ida told you about Euclidean distance. There are other types of distances. Euclidean is one of them, and it's often used. And it's simple to compute because if we assume that the data is so like in a Euclidean space, like, I mean, we live sort of in Euclidean space, X, Y, and Z, then Euclidean distance is just like we would take a ruler and we would measure the distance. So we go through all the features, compute the distances, square them, and then sum them up. And that's Euclidean distance. And then Ida showed you how to construct something called hierarchical clustering. So how to construct a structure where we see where in this structure the groups or data instances that are close together, so that have this minimal distance or the smallest distance are placed together in a group. And this is great because we can take this structure and cut somewhere and say, okay, so maybe here's a cut, and then maybe we have two groups that we can explore further through some statistics like box plots or anything that we'll actually learn. The problem here with this technique is that it requires the computation of sort of like a square matrix of the distances. So we need to, in every step, right, we need to compute the distance, the Euclidean distance between all the, I mean, at the start, we need to compute the Euclidean distance between all the data that we have, right? If we have just like, if our data set has about 100 points, right? 100 data instances, this is not too much, right? Because so we have a matrix of 100 times 100, right? And I'll here ignore that this matrix is symmetrical, so that we can, the space that we need is actually 1/2 of the full matrix, right? But let's say we have 100 times 100. So 100 times 100 is 10,000. And I don't want to torture you with this, but just to understand a little bit, right? Usually the floating points in this matrix, I mean, the floating number, the numbers with the floating point are stored in 32 bytes. So basically we have 32,000 kilobytes of data. As I said, I don't want to torture you with this, but that soon becomes an issue, right? Because if we go to a slightly larger data set, let's say with, I don't know, with n equals, let's say we have 1,000, right? So 1,000 data instances. Then, then the space that we would need for just to store the distances between all the data points, we would need 1,000 times 1,000 times 32. Okay, so times 32. So that is already 32 megabytes, right? Okay, that's not much because your computer has that capacity, right? 32 megabytes is not much here, right? But that's for n of 1,000, right? But what if n goes higher, right? What if we have a like larger data set? Let's say maybe I put 100,000, right? And then we have 10 zeros, right, for the square matrix, and that's already gigabytes, right? So times 32, right, which is 320 gigabytes, right? And this is what you don't have in the computer anymore, right? So basically what I'm saying, right, is that with a large data set, like, I mean, typically of several 10,000s of instances, right, this becomes prohibitively large, right? So this matrix, this distance matrix doesn't fit into a memory of computer, right? I mean, that's one thing, right? The second thing is that, of course, we can't see something, so I'd explain you, this is called the dendrogram, this particular visualization. I mean, that also doesn't fit, right? The screen with 100,000 data instances. Of course, there are tricks, right? You can always hide a part of this data structure and then construct something that it's way simpler, and then it contains just groups. I mean, there are workarounds around that, right? But basically, the problem is I mean, not only storing this number, but computing that takes substantial power as well, right? And so people have been thinking about other techniques. One such other technique that I like to show you today. So there are two reasons why I'm showing you. I'm showing you this particular technique because I would like to point out that there are other clustering techniques that are also much faster on the bigger data than hierarchical clustering. And I would also like to show you some tricks with the clusters. So the idea that I'm going to present to you, right, is best presented in a 2D space, right? So I'll assume, right, I have two features only. Let's say height and a weight, and then I have some people with some height and weight. These are the data points, right? And then the trick here with this method is that one needs to decide how many clusters does one want. This is hard, right? Because, I mean, it's for two-dimensional data, it's simple, but for high-dimensional data, this is really hard. But we're going to see that there are ways around this as well, right? But let's say once you decide that, okay, maybe I want to see whether there are free clusters in this data, the computer or the algorithm places something called the centroids somewhere randomly in this space. Maybe one is here, I don't know, one, let's put it here, right? And then one is here, right? So these black points are called centroids. Basically, they will be the centers of the clusters. I mean, in a most stupid way, they're put randomly in the feature space. And then, of course, we can look now, because they are centers of the clusters, right? We can actually take a look which points are close to each of these centroids. So for instance, this point here, right? So I'm circling it. It's closest to this black point here, right? So which points are closest to the green one? Well, this one is close, and this one is close, this one is close, right? But these two are closest to the orange one, right? And so are all the guys here, right? They're closest to the orange one. Well, and then the blue one has this one here. So basically what I do, right? I put the centroids somewhere, right? And then I ask, okay, I mean, which data points are the closest to these centroids? And I see actually that if I look at the blue centroid here, right, I see that majority of points that are closest to this centroid are actually on this side, what I would call a data space, right? So data space is like this combination of height and weight. And so what I'll do, right, I'll actually move this blue point to the center of the points that are closest to it, right? So basically, the new blue point is here, right? So I'm going to move it here. Okay, that's more appropriate place where the blue point should be, right? And I'll do the same with the green and orange one. So orange, I see. Okay, so there's a particular point here, right? That still attracts the orange point slightly up, right? But the majority of the other ones are down there, right? So what I'll do, right? I'll change the position of the orange centroid to somewhere here, right? So to the center of the points that are the members, so that are closest to the orange one, right? And it's similar for the green one, right? So the green probably would move somewhere here actually, because there's this point that's far away that still attracts the green one, but the majority of points are actually in this part, right? So this is what I've done. So I moved my points a bit, right? And then, so these are the new positions, right? And then, of course, I repeat the procedure, right? I again find the points that are closest to each of these centroids, right? And then I see, okay, the orange ones are all this, right? And the green ones are all this. And the blue ones are here, right? Okay, right? Because they're going to move just slightly, right? So the new position of the orange one, right, will be in the center of these points here, down here, right? So it will be somewhere here, right? That's going to be the orange one, right? The blue one will essentially stay almost where it is now, right? The blue one had something on the left or not, but the blue one would be now in the center here, and the green one is going to be here, right, in the center. Now I can repeat the procedure, right? But I'm actually going to find out that these points won't move anymore because they are now, right, the solution has now reached a stable case. So nothing changes anymore, right? So each of these points is now exactly the center of its cluster, right? Which is which is defined in a stable way, right? And that's K-means, right? And it's so I don't know if I convince you into anything, right? But I mean, in this way, I actually found that there are 3 clusters. So one cluster is here, right? The other one is here, and the third one is here. And I also found the centers of the clusters, which are the centroids, right? This technique for clustering is also called K-means. And K, right, stands for this all-important parameter that the user, right, the data scientist or whoever uses this clustering has to define this parameter ahead, has to decide what is K, right? And so here, right, in this case, I decided that K is going to be equal to 3. Okay. I could decide also that K would be equal to 2 or 4 or 5, right? But then I would get, of course, different results. I also need to tell you why is this faster than why is this faster, or why is it also less demanding in terms of the memory to hierarchical clustering? So in hierarchical clustering, if we took the data and then computed the distance matrix, the distance matrix was basically of the size n squared, where n is the number of the data instances. And here we compute. So how many distances we compute here? Well, we compute n distances, so distances to the n different data instances, right? Times k, right? But k is equal to 3, right? So even if n is 100,000, right? So the number of computation in each step is not 100,000 squared, right? But it's 100,000 times 3, right? Which is 3. Even if I have 1 million points, right? The number of computations at each step is that 3 times that. And this is not much for computational power. Also, I don't know. I'm not showing you anything yet, right, in terms of how to use this. But I'd just like to say that this algorithm converges fast. So once you set up the initial positions of the clusters, the initial positions of centroids, this technique will converge within several hundred steps at most, right? So the computation won't take too long. I remember the first time I really used it on some large data set was a telecom data set of around 1 million users. They were described with, I don't know, about 500 features. And even my own method in Python that wasn't really optimized took me, I don't know, found clusters in 20 seconds. So this is not, this is it's a very fast technique, right? What do you think are so here I'm not saying that this is it solves all possible problems, right? Because it doesn't, right? And what do you think, just intuitively at this stage, before we dive into what are the problems here? Why K-means is not the only clustering method that everybody would use? What do you think? What do you think is a problem here? First problem is K. What's the value of K, right? Cool, because here in 2 dimensions, right? This is very simple, or we would just need to visualize this data in a scatter plot, because our eyes and brains were designed actually to detect the patterns in 2 dimensions. But the data does not lie in 3 dimensions only, right? So even for a simple data sets is very hard to determine, very hard to decide what is K, right? Here, of course, I cheated, right? Because I draw the data in such a way that it's easy, right? To guess. I mean, even I mean, the clusters were well defined, right? But what if the clusters are not well defined? What if I have something like this, right? What if I have noise, right? Or maybe undefined clusters, right? Definitely we would run into problems here, right? But with any clustering technique, right? So maybe K-means clustering would actually work fine because they would define these spherical regions where even with noise, I would have the clustering. K-means clustering always finds K clusters independently how the data looks like. So I gave you a simple case, right? And it's, I said that this clustering is initialized with maybe this idea of just randomly initializing the data points is not a good idea. Maybe I initialize it in a way that I don't find clusters even if they are there, right? So initial placement of centroids. But I have to give you an example of this, right? So maybe that's a problem as well, right? So the solution does not converge to optimal clusters, right? That would be one problem. And maybe there are some others. But it's time for me to show you actually how this works. So such that I don't talk too much about the theory. What I'm going to do here in orange, I'm going to actually paint my data. I'm just going to do the experiment like the one that I was doing here, let's say on a paper, right? I'm actually going to paint some data for clustering. So maybe I take a brush, paint some data here, and then some data here, and then, I don't know, leave it like this, and then some data here, right? Okay, so I'm again cheating. I'm actually, so this data looks like to a human eye, right? That it has 3 clusters, and then I'm going to use something. There's a widget in the educational toolbox where it says interactive Kmeans. So this is just to showcase actually this technique, right? So we start with some random position of centroids, like this one, right? So each centroid has, so these are the links to the closest, or actually for each data point, we decide which is the closest centroid. This is fine, right? And then we recompute the position of centroids. And then we reassign the membership. So now probably the blue one is going to take some of the green ones here, right? And the red one is just fine, right? And then repeat this, right? And then reassign the membership. And now we are done, right? So here in 2 steps, right, we were able to solve this problem, right? Is this good clustering? Yeah, it's just like the one that I would draw by hand, right? Okay, let me try with some other position of centroids. Let's say, so let me try with this position of centroids. So I would randomly assign the position of centroids at the beginning, right? And then I would recompute this. Well, here it's going to be a saver. Here it's going to take some more time, but here eventually, right, the blue one will slowly take off. Maybe I have to redraw my data a bit. Select these 2 and take them away. And then I have the initial position of the centroids is like this, and then I recompute them, and then it stops here, right? Is this a good clustering? No, it's not. One thing that was a cluster, right, was split into 2 clusters, and here where we see that there are 2 clusters, the green one took over, right? So it's likely, right, that upon the wrong position of upon the wrong initial position of the centroids, I converge to the clustering that is not optimal one. Any idea of how would I put the centroids in a more informed way? Depends on the density of points, right? So you would find where the points are the denser, right? And then do what?
And then start with centroids there, those hotspots there.
Yeah, but maybe the densest points are here. And so what do? I put all the centroids here. Finding where the points are dense, it's quite hard. It's quite computationally demanding, right? Any other idea that it's maybe simpler? So where do I put the first centroids, right? So I'm starting to put some centroids. They're here, right? So I'm going to take a blue one, right? I would like to put it somewhere. Where do I put it? I put it in the center. I put it here, I put it here, I put it here. Where do you want me to put the blue one? To the extreme, perhaps, right? Okay, so this is like, I can put it at the point, right, which is the most far away from everything else, right? And where do I put the second one? A red one. I decided I'm going to put the red one to the point that is as far away as possible from here. So maybe down here, maybe this one, right? And when do I put the green one? So here, right? So at the point which is the farthest away from these two, right? And that guaranteed, right, will always converge, right, nicely. So people have noticed that. Of course, the problems are the outliers, so the points that are far away simply because of the noise, right? And they term this. So instead of doing that, they are actually. I mean, the real algorithm that does this, right, says, okay, we're gonna put it. We're gonna actually define a set of points, not just one, which are the farthest away, right? And from this, we're going to randomly choose where we're going to put the centroid. And we're going to repeat this procedure, I mean, the placement and the clustering 10 times. And then, right, we're going to choose the best clustering, for which I didn't tell you how we do that yet, right? But there's going to be a neat trick to do. I mean, this particular trick, right, of placement has this funny computer scientist name, right? So Kmeans clustering has something called initialized with Kmeans ++, right? But this Kmeans ++ is exactly what I told you, right? Put initial centers of the clusters as far away as possible, and then actually repeat, rerun the stuff 10 times, and do the clustering. So now we can see, okay, we have a fixed number of clusters, free, right? We can actually see that in a scatter plot. So I'm gonna, the color will be the clusters, and these are the clusters, right? So this is what Kmeans does. Okay, and that's nice because this is what we expected, right? Of course, if I lower the number of clusters to 2, right, or to 4, to 2, then I get something like this, right? So this is not, I mean, here I'm seeing that, okay, I got one cluster right, but the other two are just simply, there should be 3 clusters here, right? Or if I go up, right, to 4 clusters, then the clustering structure breaks down, right? And I would see that nicely, right? So the advantage here is that if I have my data in 2 dimensions, then I see this, right? But if the data lies in several dimensions or in multi-dimensions, then it will be very hard for me to notice that the 2 clusters are actually close to each other and maybe they should be joined, right? Whereas, of course, if I have the hierarchical clustering here, right? And then I need to zoom in, right? I would definitely see, right? I don't know why it draws like this. I would definitely see that there are 3 clusters and no more, right? There are not 4 clusters here because 3 are so, it's so nice to cut here, right? So compared to, I mean, if I compare these 2 techniques, right? Hierarchical clustering and K-means, then I see that hierarchical clustering has this particular advantage that it can graphically represent the clustering. So in a dendrogram, right? And this is great to explore. And I would need to, I mean, I would know how to decide which numbers of clusters I have. And Ida has showed you yesterday that it's also nice to explore what are the clusters and so on, right? But in K-means, I have almost like a black box, right? So I do the clustering and then that's it. Usually you have this trade-off in machine learning, right? Either you can interpret something like in a dendrogram, right? But then maybe the stuff is too slow, right? Or not expressive enough, or you have something that computes fast, right? But you cannot interpret. You cannot understand what it does, right? Although regarding the interpretation, right? So although you don't see any clustering structure in K-means, you can still interpret the results, just like, I don't know, maybe let's do a neat trick here. Just read the data. So I think Ida showed you yesterday the zoo data set. So I'm going to take the zoo data set again. So remember, this was the data on the animals, right? The animals, different animals had hair, feather, sex, milk. So these were all the features that told us how the animals looks like or what it does, right? And then I can do the Kmeans clustering. Here I'm blank. I have no idea how many clusters I have. Just by looking at this data, I'm completely lost. Luckily, like in half an hour, I'll show you that we are not completely lost always. So there are means to think about the clusters. Actually, but here, just looking at the data, I'm lost. And maybe, I don't know, I'm just going to run with 4 clusters, right? So the only thing that I can do really is then I can say in a box plot, right? So the subgroup will be the clusters. And maybe, luckily, with the animals, I have the type, right? And here I can observe, I mean, if this makes sense. And luckily here, this seems to work fine in a way, because I have 4 clusters. This is how I decided. So this is how I set the K, right? I have 4 clusters. The majority of the cluster, I mean, in cluster 1, I have most of the mammals, right? And then in cluster 2, I have the fish, right? But some amphibian and mammals and reptiles, right? And then there are mostly birds in the first cluster, and then a mixture of all the invertebrates. All the insects are in the 4th cluster, and all the invertebrates are in the 4th cluster as well, right? So this would give me a hint that maybe I need 5 clusters. Maybe this group will break down, right? And also it's interesting to see what mammals are here, right? So what mammals are close to fish, right? What do we expect here? So I can go to the data table with the, so it's here, there's dolphin and porpoise. That's great, right? So no surprise here, right? I also found out that there are 2 mammals, right, that look like a fish, which is great. And maybe I should not stretch the bars just to know that what is the true numbers of the isomorphs in the clusters. Maybe I go to 5 clusters, and then I see that, well, yeah, not happy with that. So the insects and invertebrates still stay together. Fish got its own clusters still, right? And then amphibians and reptiles are here, right? So it's hard for me to decide whether this is better than 4. So it's either, I need to type this down. 4, it's like this, and 5, it's a bit different. All right. So basically what I'm saying is that I can also check out, right? So based on a cluster, right? What about the X, right? So maybe I go to 4. What about the hair, right? And I see, okay, there's one cluster where everybody has hair, right? And then the other 3 that where they don't, right? And they lay eggs in the other clusters, but not in the first one, with one exception. And that is, the exception is platypus. Platypus is a mammal that lays eggs. Okay. Yeah. This is sort of hard, right? So hard because I need to spend a lot of time in trying to analyze what the clusters are in order to decide what is the K. So the question is whether is there any help here in finding out the right K? Okay. And maybe I'll show you so what Ada showed you yesterday, right? So there's this technique called Silkwet. Okay, so let me provide you with some questions here. So let's say this is my data now. This was the clustering assignment to the data points that I have. They live in 2D, so it's simple for us to analyze. And here the question would be, so I have this data point A, and then this data point B, and the data point C for the black cluster. And I would like to know, or maybe I have this so more obvious. This is A. Okay, so this one is A, this one is B, this one is C. So which of the 3 points is more central to the black cluster? A is the central, it's more central to the black cluster. Why? What does it mean it's in the middle? So basically what you would do, right? I mean, what you're suggesting is I measure the distance to all the other black ones, right? And let's call this distance A, right? And for the point to be central, I would like to minimize this distance, right? So A is the distance to points, I would say the average distance to points in the same cluster. Okay, let's call this A. Okay, all right. Why is A also, why is B not central? There's also one other stuff that I need to check, right? So B is also close to the closest cluster, right? Not to the green one, but actually to this red one, right? So let me have another thing here, right? So another quantity that I will say, and I will say that these are, I will mark these points with the index I. So I would say that I have AI and BI is average distance to the closest cluster, to the points in the closest cluster. For a point to be central, right? How do we like AI to be? I mean, AI should be small or large for the points to be central. AI should be small, right? And BI should be large, right? So the farther away I am from the closest cluster, the better, right? I have these two numbers now, so A and B. But the problem is I usually like only one number because I two numbers, I don't know what to do with that, right? And maybe I have something like I have BI minus A1, AI. So I would like BI to be large and AI as small as possible, right? So I would like this quantity to be as large as possible, as large as possible, for a point to be central to the cluster, okay? But usually in the data science, we like things to be normalized in a way that I would say that, okay, there is this number that ranges from 0 to 1, let's say. And so I do that if I compute the maximum of the two quantities, this number is going to be called a Silkwet, SI. And it's going to be in between 0 and 1 for any reasonable clustering assignment. When it's going to be 0?
B and A are equal.
Yeah, so probably for this point here, right? This point, it looks like almost equally distance to the closest cluster as it is to its own cluster. So probably the silhouette of this one will be 0 or close to 0, right? And there's going to be, this one is going to be 1, right? So the silhouette will be 1, where when BI is very, very large and AI is almost like a 0. So it's going to be BI divided by BI, which is 1, right? That means, so the central points will have a silhouette that's going to approach to 0 if the closest cluster is away from everything. That's great. And we can actually compute the silhouettes. There's a widget. I think I just showed you yesterday, right? There's a widget that computes the silhouettes okay, not by type, but I'm gonna do it by the cluster. So I have clusters, and these are my silhouettes. Yeah, I'm surprised. This is actually a good clustering, right? So all the silhouettes are positive. Nothing is misclassified. So which ones? Well, let me give you, actually, this is, it's always hard if the data lies in too many dimensions. Let me paint the data. So I'm gonna use the painted data again, and maybe put some more, right? Like this, and then I'm gonna do the Kmeans clustering here. And then I'm going to request 3 clusters, not 6, but well, that's okay. 3 clusters. And then I'm going to use the scatter plot. And this is the K-means clustering on this data set. But I would also like to see what the Silkwets are. The Silkwets are here. And then I would like to see where the centers of these clusters are. So by saying, okay, whatever I'm going to select in the Silkwet is going to show up in the scatter plot. Okay. And so maybe, oh, here are the centers of this is the central point of the blue cluster. See, like expected, right? And these are the 3 central points of the red cluster here. Central meaning, okay, they're within the red group, right? But away from everything else, right? And which is going to be the central green point? I would say that probably either this or this one, right? So let's check out. It's this one, okay? And what are the outliers, right? Sort of like the outliers. So there are these, so that for the green cluster, this point is actually most on the border, right? It's still closer to the red ones, but okay. And so for the blue cluster, the outlier is here, right? Okay, this simply means that this works, right? So it makes sense what we have. How we would like, what kind of shape we would like for these Silkwets for kind of good clustering? What do we expect? What kind of shape? What kind of shape of these Silkwets? What kind of shape of this graph we would prefer? We would like to have this sort of like fat here, right? And then just a few maybe points having a low Silkwets, right? So these graphs are sort of okay, right? I mean, they should be, these Silkwets should be high, mostly, right? So the Silkwet has a strange name, but somebody thought that basically this graph shows sort of like a Silkwet, a shadow, right? And these are sort of shadows, and this is why it's called the Silkwet score. Yeah, maybe if I don't know what happens if you can play on your own, right? But what happens if I mess up this, right? And then I see I lose the shape, right? So there are now a number of points, right, with the poor Silkwets, okay? So if the data becomes mixed up, right, then I have a problem, right? I would also have a similar problem if I would say that, so here, right, instead of 3 clusters, maybe I like 2. Come on. So then I have 2 clusters like this, right? But I see that the Silkwets for the red cluster, some of the Silkwets are really low, right? So there are 2 things that I like with this particular method. I like clusters where the Silkwets are large, right? I can actually take all the Silkwets and compute the average Silkwet out of this course. And then I would claim that the clustering that I like best is the one with the highest average Silkwet. And this is what this widget does, actually. So I'm gonna now remove this. Okay, so basically what I do, right? I compute the Silkwets for all the points, and then I compute the average. And this is the score of my clustering. So what K-means can do, right? We can tell instead of the fixed number of clusters, I can evaluate the clusters from k equals 2 to k equals 8, okay? And then I plot here the average Silkwet score for each cluster. And then I see, although there are not major differences here, right? But then I see that k equals 4 has the largest Silkwet. So this is now becomes a Silkwet computation becomes a neat trick to estimate the quality of the clustering, and then to decide how many clusters do I want, okay? And it turns out that this is 4. So I like 4 clusters on this data. And so this is the first use of the Silkwet. The second use of the Silkwet, of course, is that to find out for each of the clusters what are really the outliers, right? So here I see that this clustering technique, I mean, which cluster do I like best from all the clusters here? Which cluster is the most homogeneous one? The blue one, because the Silkwets are the highest, right? It has some outliers here, right? Maybe let's check the free outliers here. So the blue one, okay, so maybe I'm gonna check out the data. Oh, so this is actually a cluster of mammals, okay? But there are some sort of like exception, right? And that is platypus, seal, and sea lion. Maybe if I go a bit higher, right? Okay, there are some more, right? Like a vampire, okay. So, but platypus, seal, and sea lion, right? These are all the mammals that live in the sea, right? And so they're sort of like probably close to the fish, right? And not exactly in the mammal section, right? And the typical mammals are, I don't know, antelope and leopard and lion and puma and wolf, right? And the others, right? These are sort of typical mammals, right? And typical representatives of the second clusters are fish, right? Bass, catfish, piranha, and so on, right? But there are some outliers here in this cluster as well, right? Which are dolphin and porpoise. So they were clustered within fish cluster, right? But these are actually mammals, okay? And then, I don't know, these are the birds, right? Crow, hawk, lark. And there's some outlier here, right? Which is a reptile, which is a tortoise, right? And why is it within bird section? It lays eggs, right? So maybe something like this, right? And then there is this cluster that we see, it's sort of like the most messed up because the Silkwets are small, right? And so this is like sort of like a mixture of insects and invertebrates with flea, slug, termite, worm, right? And there's some things that really don't belong here, like a scorpion, right? Okay, so I would not like to go much deeper here because I would like to go to other things that we need to learn. But I find this Silkwet great. I mean, it's like one of the simplest. It's like I mean, there are other statistical approaches, much more thorough in a sense of math, right? But Silkwet is the simplest stuff, right? You can do, right? I mean, it's so simple that I was able to explain it to you in terms of the math, right? In 10 minutes. It's the simplest stuff that people use when evaluating the clusters. So it's good when you try to estimate the number of clusters. But I really like it in combination of once the clustering is done to find out what are the central points and what are the outliers, right? It's the simplest way how to do that. And it's a great tool for exploratory data analysis in the sense that you try to explore what the centers are and what are the outliers, and you try to think about the data, right? So there's no statistics involved. It's just simple tool to satisfy the curiosity, right? So that's on Kmeans, and basically so you see the difference between Kmeans and hierarchical clustering. For me, the biggest difference is that hierarchical clustering has this dendrogram that I enjoy to see, right? I like to see the dendrogram. The dendrogram really tells me a lot about the data, right? So the dendrogram, right? Not the hierarchical clustering. Oh, I put discretize, sorry. Distance, and then hierarchical clustering. So this is and I should use the word. So this is the clustering of the animals, right? And it's nice. And if I give it a name, right, and then maybe zoom out a bit, I see that there is. So in this dendrogram, I see that there are like there's even a group like this dolphin, porpoise, seal, and sea lion, right, which are mammals, right? But in a way, they are close to fish, right? So while I see that here, right, I'm sort of surprised that this branch here, I mean, the dendrogram has its limitations, right? I don't know. I mean, it looks to me, right, if I'm sort of not precise, right, that these dolphin, purple seal, and sea lion are sort of like in the center of the mammals cluster. But they are not, because you can always rotate the branches around, right? So the, I don't know, the fish are somewhere here, right? These are the fish. And one would say that the dolphins, porpoise, sea, and sea lion are really far from the fish, right? Whereas we know that this is not the case. So interpretation of the dendrogram is sort of tricky in a way that you should not think about the distances between the groups of different clusters. So the dendrogram, the only purpose is that, okay, here's the clustering structure and I should take it, right? But I wouldn't know how far away are each of the branches, like this one and this one. The dendrogram tells me nothing about this. So it sort of misses some points in the structure of the data, right? It misses it doesn't tell me about the distances. So the dendrogram speaks about the clusters, but then once I have it, I cannot relate a cluster here to a cluster here because there's no information about that in the dendrogram. So if I want to compare these two, there's nothing I can say about that. And we need different methods, right? So, okay. I like hierarchical clustering because the dendrogram, right? It doesn't do well on the large data sets. For that, I need K-means clustering, right? K-means clustering is problematic because I need to define the K, but we invented this Silkwet plot, right? So there's help, right? And oh, by the way, the Silkwet plot is also good because I can find the inliers and the outliers. And then fine, right? But then in the whole picture, right, there's something missing because, so with K-means, I really don't see the structure. I see the structure in hierarchical clustering, but it's sort of sometimes deceiving because the only thing that I can reason is about the clusters and not about the relations between different groups, right? So there's something still missing, okay? This is not the whole picture.